The objective of this video is to introduce and analyze the operation of the buck-boost switch mode converter. The basic idea of the buck-boost converter is that it's able to realize an output voltage that's either higher or lower than the input voltage. So this provides the most versatility in terms of a voltage range that you can realize. However, as we'll see towards the end of today's video, this comes with a certain penalty. This converter is a little bit more complicated to understand at a first pass, so we'll start by simply assuming that it works and then work backwards to analyze the details. So starting with the single pole double throw converter as sketched on here, I've labeled an input source as Vn and an output source as Vout, or our equivalent load. Let's now sketch the current waveforms. Since we're taking power from the input source and bringing it to our load, we have an input current that's going to follow this path right here, In. And since we're delivering power to our load, our output current has to flow into this voltage source, Iout. And so we can see from our labels here that our pole current must be positive. That is, we're always going to have a current in this direction through our inductor. So the semiconductor realization is going to correspond to IP greater than 0, and clearly our throw voltage is equal to Vin plus Vout is greater than 0 as well. So we can go from this single pole double throw configuration and draw the actual semiconductor realization. And on this diagram we can add our input and output current and various other waveforms. And similar to the buck and the buck-boost converter, or really any single pole double throw converter, we can consider the converter operation as having two distinct states based on whether the MOSFET is conducting. So based on whether the pole is connected to the top throw or the bottom throw. In state 1, our MOSFET is turned on, and this effectively places our inductor in series with our input voltage source. In state 2, our MOSFET is off and our diode is on, which places our inductor in series with our output voltage source. So we can again construct our table comparing the two states. And we'll define our duty ratio similarly to the buck and the boost converter as being the duty ratio of the MOSFET, which is also the duty ratio of the pole being connected to throw 1. So D is the duty ratio of the MOSFET, and it's also the duty ratio of the pole being connected to throw 1. So the time that we're in state 1 is D times our switching period, and the time that we're in state 2 is 1 minus D times our switching period. Because if we're not in state 1, we must be in state 2. The voltage blocking requirement for the diode and MOSFET are a little bit more complicated to consider in this circuit. So you can see that, let's adjust things, we have a little more space here. So when we're in state 1, we're blocking voltage across our diode. So if we were to put a multimeter and measure the voltage between this point and this point, it would be the same thing as measuring the voltage between this point and this point, which is to say it's equal to Vin plus Vout. Is Vin plus Vout. The MOSFET voltage is 0, or rather it's the voltage across the channel resistance of the MOSFET due to the current. When we're in state 2, now our MOSFET is blocking and our diode is conducting, so our diode has to block 0 volts, and the MOSFET has to deal with the voltage between this node, and this node, which is again V in plus V out. The voltage across our inductor in each state is given as V in for state 1 and a negative V out for state 2. The current through our inductor is equal to our pole current, and it clearly must be increasing in state 1 since V in is positive, and decreasing in state 2 since there's a negative V out applied across the inductor. Our input current during state 1 is equal to our inductor current, and our input current during state 2 is equal to 0. Our capacitor current during state 1 is simply going to be the negative of our output current because the capacitor is completely taken out of the branch. There's no current from the inductor along this path. The capacitor current during state 2 is equal to our inductor current minus our output current. So in state 1, the inductor current is taking this path, and in state 2, the inductor current is taking this path. Let's now write our steady state voltage and current expressions for each of the devices. Our throw voltage is clearly going to be the sum of V in plus V out. And our pole voltage, the average of our pole voltage is equal to our output voltage. And we know that the pole voltage can be related to the throw voltage by multiplying it by the duty ratio. We can rewrite this to find an expression for V out in terms of D and V in, which is the equation that determines how our output voltage varies as a function of the duty ratio with respect to our input voltage. So you can see from this expression that you're able to obtain, as you sweep D from 0 to 1, you're able to obtain a range of output voltages from 0 to infinity volts. Our throw 2 current is equal to our output current, the average of our output current, which is the average diode current. Our throw 1 current is equal to our input current, the average of our input current, which is the average MOSFET current. Our pole current, the average of our pole current is equal to the average of our inductor current, which is equal to throw 1 plus throw 2, so therefore I in plus I out. And this is a key difference from the buck and the boost converter in that the average current of our inductor is the sum of our input and output currents. We can use the power conservation equation to find our input current as a function of our output current. So using eta, where eta is efficiency, times our input power must be equal to our output power. This is just saying that output power plus losses must equal the input power, or in other words, efficiency times input power must equal the power that we get out. And finally, we have an expression for our input current in terms of our duty ratio and our output current. So we were able to use the same analysis techniques, that is, the conservation of energy and Kirchhoff's current law, to derive our steady-state operating conditions for the buck-boost converter. These are the same conditions that we used in the boost and the buck converter analysis, just applied to a slightly more complicated converter. A few odd details to point out here is that while our throw voltage is equal to V in plus V out is actually a variable based on what you choose your duty ratio to be. So I made the remark that you can achieve an output voltage of 0 to infinity volts. Infinity volts clearly corresponds to when you have a duty ratio of 1, because you have V out equals 1 divided by 0. This is not a realistic thing to achieve, and it's something that has to be monitored with a buck-boost converter. If your duty ratio gets too large, you can easily exceed any reasonable device ratings for your design and actually cause a little explosion on your circuit. Let's now sketch the operational waveforms for the converter. Starting at the top, we'll sketch our sawtooth carrier with a duty ratio. And next we'll sketch the signal for our MOSFET gate. Remember, the MOSFET's going to be on when the duty ratio is greater than the carrier and otherwise off. And when the MOSFET's on, we're in state 1. Otherwise, we are in state 2. Next, we can sketch our inductor voltage. And the inductor voltage is equal to V in when we're in state 1, and a negative V out when we are in state 2. Our inductor current has an average value and a ripple component, just like the other converters. In state 1, the current increases due to the positive voltage applied across the inductor. In state 2, the current decreases, and so on and so forth. And just as on the other converters, we can calculate this ripple component by using the differential equation that governs an inductor and integrating either area A or area B. Next, we can sketch our diode current. The diode is off in state 1 when the MOSFET's on, and then the diode starts conducting the inductor current in state 2. We can sketch our capacitor current, which is equal to negative I out in state 1 when the output circuit is disconnected from the inductor, and it becomes equal to ID minus I out in state 2. And finally, we can sketch our input current. So our input current is this red arrow in state 1, and it's non-existent in state 2. So in state 1, it follows the inductor path, and then in state 2, it does not exist. And so this is different from the boost converter, where the input current was continuous. It was always equal to the inductor current. In the buck converter and the buck boost converter, the output current is discontinuous, and depending on your application, you may need to add an input filter, as we talked about for the buck converter. So as we talked about for the buck converter and the boost converter, you can use your capacitor current waveform to calculate and estimate your voltage ripple on the output. Well, we won't be doing that in this lecture.